All right, so welcome to another deep dive. Today, it's all about computer and technology systems.
Yeah, it's easy to get lost in the weeds with all the tech jargon out there.
Totally. So what we're aiming for today is to lay out a really clear map of the essential learning aims.
Exactly. We've gone through a ton of material stuff on the very basics of computers, all the way to how data flows within a system.
And by the time we're done, listeners, you'll have a rock-solid grasp of the key concepts. You'll know what you really need to learn to understand the digital world around us.
That's the goal. So let's start with the fundamentals. What are we really trying to understand when we talk about a computer?
Yeah, break it down for us.
Well, the key learning aim here is to see a computer as a machine built for processing digital data. That's its core function.
Okay, so it's all about data.
Right. Now, a technology system, that's the bigger picture. The learning aim there is to recognize it as the whole package. Hardware, software, all the peripherals like screens and printers.
And don't forget those power supplies and communication links, too.
You got it. It's about understanding how all these pieces work together to make the technology function.
It's like an orchestra. You need all the instruments playing in harmony.
Perfect analogy.
Our sources also emphasize understanding how these technology systems are actually used in the real world.
Absolutely. The learning aim there is to see how they're applied across a bunch of different sectors: construction, finance, healthcare.
Manufacturing, too. That's where things like CAD/CAM and robots come in.
Right. And we can't forget about retail, which is constantly changing thanks to new tech. The key is to see how technology is shaping these industries.
It's not all sunshine and roses, though. We also need to understand the potential downsides, the issues.
For sure. So the learning aim regarding issues is to be aware of the health and safety concerns.
Things like making sure your workspace is ergonomically sound.
Yeah. And then there's the whole realm of security, passwords, different levels of access to information, all crucial for protecting data.
We also have to consider the environmental impact of all this technology.
That's right. Sustainability is a huge concern. And then there are the ethical dimensions, too, like privacy and copyright in the digital age.
It's about understanding how to use technology responsibly.
Exactly. Now, looking forward, it's also a key learning aim to understand why organizations need to keep developing these systems.
Why is that so important?
Well, organizations that want to stay ahead need to leverage technology. It can give them a competitive edge.
And it can save them money, too, right? Automation, efficiency, all that.
Exactly. The aim is to understand how technology can lead to improved performance for organizations.
So the takeaway is that tech development is essential for staying relevant and competitive.
Absolutely. Okay, so we got the big picture. Now let's zero in on the physical tools, the hardware.
The tangible stuff you can actually touch. What's the main learning aim here?
It's to understand the different types of hardware devices, their features, what we're used for, and what it means to actually use them.
So we're talking about things like PCs, laptops, tablets, servers.
All of that. And don't forget about games consoles. Those are essentially specialized computers, too. The aim is to get a broad sense of all the forms technology hardware can take.
Now let's talk about how we get information into these systems' input devices. What do we need to understand about them?
The key is to understand their role in getting data into the system. Think about things like keyboards, mice, touchscreens.
Sensors, microphones, scanners, digital cameras, those are all ways of feeding data into the computer.
That's right. Each device has a specific function in translating real-world information into a digital form that the computer can then process.
And then once the computer has done its work, we need ways to see or interact with the results. That's where output devices come in.
Exactly. The learning aim here is to understand how those processed results are presented to us, or even how a computer can control physical actions.
So we're talking about printers, speakers, screens, projectors.
Yep, even things like force feedback devices and actuators, which can create physical movement. The goal is to see how these devices make the digital tangible, something we can experience.
And of course, we need to store all that data somewhere. That brings us to storage devices.
Right, we're aiming to understand the different ways data can be stored for later use. So there's your solid-state drives, your SSDs.
Those are the super fast ones, right?
Yeah, generally speaking. Then you have optical media like CDs and DVDs.
And the good old-fashioned magnetic hard drives.
Exactly. The learning aim is to understand the basic characteristics of each type and when you might choose one over another.
It's fascinating how so many modern devices can do both take information in and show it back to us.
Yeah, that multifunctionality is a key characteristic of modern technology. Like a touchscreen, you can input commands by touching it, and it also displays information.
It's input and output all in one.
Exactly. Now, it's not just about individual devices. We also need to understand how hardware and software work together to create those automated systems we see everywhere.
Like self-service checkouts or those robotic arms on a production line.
Exactly. The learning aim is to grasp how those systems combine hardware and software to perform tasks automatically.
Those automated systems rely on specific devices to capture data. What are the key things we need to learn about those devices?
The main learning aim is to understand what they do and how they streamline the process of getting data into the system. So we're talking about barcode readers, magnetic strip readers for things like credit cards.
Optical character readers, OCRs, optical mark readers, OMRs. Those are used a lot for processing forms, I think.
Right, and then you have RFID systems, which are used for tracking things automatically.
Okay, so we've got all these devices. How do we know which ones are right for the job?
That's a crucial learning aim, being able to select the most suitable hardware for a specific need. And not just picking something randomly, but actually being able to justify your choice.
So why this type of printer over that one? Why this much storage space?
Exactly. Being able to explain your reasoning is key.
Now let's move on to how all these devices talk to each other. Computer networking.
Right. The fundamental learning aim here is to understand the basic concepts of networking, how those networks are used, and what it all means.
So first we need to understand the different types of networks, like LANs and WANs.
Exactly. A local area network, or LAN, connects devices in a limited area, while a wide area network, or WAN, can span much larger distances.
We also have personal area networks, or PANs. Those are for connecting devices that are really close together.
Like your phone and your headphones.
And then there's mobile broadband, which gives you internet access wirelessly. The learning aim is to recognize the scale and typical uses of each network type.
Right. Now, what are some of the most common ways we use these network systems?
Well, sharing resources is a big one. Multiple users can access the same printer or software.
Yep. And data sharing, being able to easily exchange information between devices.
Don't forget about entertainment, too. Streaming, online gaming, all that.
Right? And then there's basic communication. Email, messaging, browsing the internet. All these things rely on computer networks.
It's amazing to think how much we rely on networks these days.
Absolutely. And a key learning aim is to appreciate the benefits they bring. Better communication, collaboration, more efficient use of resources, and of course, access to a wealth of information.
With all our devices connected in a PAN, it's important to keep the data consistent across all of them.
Right, you want your contacts, calendars, and files to be up to date on all your devices. That's why data synchronization is so important.
All right, we've talked about how devices connect, but how does the data actually move between them? What do we need to understand about data transfer?
The key learning aim here is to understand the basic concepts, the processes involved, and the implications of different methods.
Oh, we have wireless methods and cabled methods.
Exactly. And the choice often depends on the user's needs and what they're trying to achieve.
What are the main wireless technologies we should aim to understand?
Wi-Fi and Bluetooth are the big ones. Wi-Fi provides network connectivity over short to medium distances, while Bluetooth is typically used for short-range connections.
Like connecting your wireless earbuds to your phone?
Exactly. Now, for cable data transfer, there are three main types of cables to understand.
Okay, what are they?
You have optical fiber cables, which are known for their high speed and long distance capabilities.
Those are the ones used for high-speed internet, right?
Often, yes. Then you have unshielded twisted-pair UTP cables, which are commonly used in wired Ethernet networks.
And coaxial cables, which are used in various communication systems.
Right. The learning aim is to recognize these different cable types and their general uses.
So we've got wireless and cabled methods, each with its pros and cons.
Exactly. Wireless offers flexibility and mobility, while cabled connections tend to be faster and more reliable.
So you have to weigh those trade-offs when choosing a method.
Right. Now, let's shift gears and dive inside the computer itself.
Time to crack it open and see what makes it tick.
Learning Aim B is all about understanding the internal components of a computer, how data flows between them, how it's processed, all that good stuff.
Let's start with the motherboard. What's the key takeaway there?
The learning aim for the motherboard is to understand its role as the central hub that connects everything else. All the other components plug into it.
It's like the backbone of the computer.
That's a good way to think about it. Now, the CPU, the central processing unit, that's the brain of the computer.
The one doing all the heavy lifting.
Right. The learning aim is to understand its function as the main processing unit. And it's made up of several key parts.
Like the ALU, the arithmetic and logic unit, which handles all the calculations.
Yep, then you have the control unit, which manages the flow of instructions.
And registers, which act as temporary storage for data that's actively being processed.
Exactly. Now, we also have different types of memory inside the computer, RAM and ROM.
What's the difference?
RAM, or random access memory, is the computer's short-term memory. It's used for storing data that's actively being used by programs.
So when you close a program, the data in RAM is gone.
Right. It's volatile memory, meaning it needs power to retain data. ROM, on the other hand, is non-volatile.
So that data sticks around even when the computer's turned off.
Exactly. ROM includes things like flash memory, which is often used to store the initial boot instructions for the computer.
Then there's all the specialized hardware for handling things like graphics, sound, and video.
Right. The learning aim here is to understand that there are dedicated components for those tasks. You have GPUs, or graphics processing units, for rendering images.
Those are especially important for things like gaming and video editing.
Absolutely. And then you have sound cards and video processing units. These components are designed to handle specific tasks efficiently.
And all that processing generates heat, right? That's where heat dispersal systems come in.
Exactly. The learning aim is to understand how systems like fans and heat sinks prevent those critical components from overheating.
And that helps keep the computer running smoothly and prevents damage.
Right. Now, we also talked about storage devices earlier. Those are considered internal components, too.
So your SSDs, optical drives, and hard drives, they're all connected to the motherboard inside the computer.
Exactly. They provide long-term storage for the operating system, applications, and all your data.
All these internal components work together to determine how well the computer performs.
Right. The learning aim is to understand how the characteristics of those components affect things like speed and responsiveness.
So a faster CPU, more RAM, and a faster storage device will generally lead to a better user experience.
Exactly. And when you're comparing different computers, you'll see all sorts of different specifications.
So it's important to understand what those specifications mean, like clock speed, cache size, number of processing cores.
Right. And for mobile devices, it's important to understand the implications of system-on-a-chip, or SoC design. That's where many components are integrated into a single chip.
And how does that affect things?
Well, it can impact both performance and battery life. Mobile systems often have to balance those two factors.
So understanding how mobile systems differ from traditional desktop and laptop systems is another key learning aim.
Exactly. Now, how about memory and storage specifically?
What are the key things we need to understand about how those features affect performance?
Well, the learning aim is to understand how the amount and speed of RAM affects multitasking. More RAM and faster RAM means smoother performance when you're running multiple applications.
And cache.
Cache is a special type of memory that speeds up data access. The CPU can access data in cache much faster than it can access data in RAM.
So a larger cache can lead to better performance.
Generally speaking, yes. And with storage devices, the learning aim is to understand the difference between SSDs and traditional hard drives. SSDs are much faster, which means faster boot times and faster application loading.
They're also more durable, right, since they don't have any moving parts.
That's right. Now, lastly, we need to understand how all this data moves between the different components inside the computer. That's where computer buses come in.
What are those?
They're essentially the electronic pathways that carry data. You can think of them as the highways inside the computer. The speed and efficiency of those buses play a role in overall system performance.
Okay, we've covered a lot of ground on hardware. Now let's switch to the language of computers. Analog and digital data.
All right, this is where things get a bit more abstract.
So what's the first thing we need to understand about analog and digital?
The key learning aim is to understand the fundamental difference between them. Analog data is continuous, while digital data is discrete.
Can you give us an example?
Sure. Think about a vinyl record. The grooves on a record represent sound waves in an analog way. They're smooth and continuous.
And a CD.
A CD stores music digitally. The data is represented as a series of distinct values, typically zeros and ones.
And why is it important to understand that computers need to convert between these two types of signals?
Because many real-world signals, like sound and light, are analog. But computers work with digital data.
So they need to be able to translate between the two.
Exactly. Analog to digital conversion, or ADC, is used to convert analog signals into digital data that a computer can process.
And digital to analog conversion, or JAP, is used to convert digital data back into an analog signal that we can experience.
Right. Like when you're listening to music on your computer, the digital audio data is converted back into an analog signal that your speakers can play.
And how is data actually represented inside a computer?
At the most basic level, it's all done using binary notation.
Which is?
It's a system that uses only two digits, 0 and 1. Each 0 or 1 is called a bit.
And a byte is a group of bits, right?
Typically 8 bits, yes. And then you have word length, which refers to the number of bits a CPU can process at once.
Okay, so how do we measure the capacity of memory and storage devices?
We use units like bytes, kilobytes, megabytes, gigabytes, terabytes, and even petabytes. A key learning aim is to understand these units and have a sense of their relative scale.
So a kilobyte is 1,024 bytes, a megabyte is 1,024 kilobytes, and so on.
Right. And how do we represent letters, numbers, and symbols in binary?
Good question.
It's done using encoding systems, where each character is assigned a unique binary code. One of the most common encoding systems is ASCII.
And our sources also mentioned learning how to convert whole numbers to and from binary. Why is that important?
It's a fundamental skill for understanding how computers work with numerical data. Being able to convert a number like 7 into its binary equivalent, 111, helps you see how numbers are represented at the most basic level.
And being able to go the other way from binary to decimal is important too.
Absolutely. Okay, we spent a lot of time talking about hardware. Now let's move on to software.
The instructions that tell the hardware what to do.
Exactly. Learning AIM-C is all about understanding the different types of software that exist.
So first off, what exactly is software?
In simple terms, software is a set of instructions that tell the hardware what to do. These instructions can be as simple as adding two numbers together or as complex as controlling a self-driving car.
And we often hear about custom-made software and off-the-shelf software. What's the difference?
Custom-made software is developed specifically for a particular user or organization. It's tailored to their exact needs.
So it's like a custom-tailored suit.
Exactly. Off-the-shelf software, on the other hand, is pre-developed and readily available for purchase. It's more like buying a suit off the whack.
And each type has its own advantages and disadvantages.
Right. Custom software is great because it can be tailored to your specific needs, but it's often more expensive and time-consuming to develop. Off-the-shelf software is more affordable and readily available, but it might not meet all your needs perfectly.
So how is software actually created? That brings us to programming.
Right. The learning aim here is to understand the basic concepts of programming and how it enables us to create software.
Our sources mentioned a hierarchical structure when it comes to software and the computer.
Right. It's helpful to think about the different layers involved. At the top level, you have application software, which is what the user interacts with directly.
Like word processors, web browsers, and games.
Exactly. Underneath that, you have high-level programming languages, which are used by programmers to write software.
And those are translated into low-level programming languages, which are closer to the machine code that the hardware understands.
Right. And at the very bottom, you have the hardware itself.
So what are the main types of high-level programming languages we should aim to understand?
There are several different programming paradigms, each with its own characteristics. Imperative languages focus on giving the computer a series of step-by-step instructions.
So it's like giving someone directions. Go straight, turn left, then right.
Exactly. Procedural languages group those instructions into functions or procedures, which can be reused throughout the program.
And event-driven languages are designed to respond to specific events, like a mouse click or a key press.
Right. And then you have object-oriented languages, which use objects to represent data and the actions that can be performed on that data.
Okay, so that's high level. What about low-level programming languages?
Low-level languages, like assembly language and machine code, are much closer to the hardware. Assembly language uses symbolic codes to represent machine instructions, while machine code is the raw binary instructions that the hardware understands.
So those are more difficult for humans to work with?
Generally, yes. They require a deeper understanding of how the hardware works, but they also give you more direct control over the hardware.
To help visualize how programs work, we use flowcharts.
Right. The learning aim is to understand how flowcharts represent the logic of a program using symbols and arrows.
So a flowchart can show the steps involved in a process, including decision points and different possible outcomes.
Exactly. And there are standard symbols used in flowcharts like terminators, connectors, processes, and decision boxes.
And being able to complete a flowchart with missing elements is a key skill.
Right. It helps you think through the logic of a program and identify any gaps or errors.
Our sources also mention some specific terms used in computer programs.
Right? Things like declaration, input, output, assignment variables, constants, subroutines, and scope.
Can you explain those briefly?
Sure. Declaration is about defining variables, which are like containers for storing data in a program. Input is the data that goes into the program, and output is the result that comes out. Assignment is about giving a value to a variable. A constant is a value that doesn't change. Subroutines are blocks of code that can be reused, and scope refers to where a variable can be accessed in a program.
It's also important to add comments to your code, right?
Yes, that's called annotating. It makes the code easier to understand for others, or even for yourself later on.
What about data types?
Data types specify the kind of data a variable can hold. There are different types for numbers, text, and true-false values.
And what about data structures?
Those are ways of organizing data. Records are collections of related data items, while arrays are ordered collections of similar items.
Okay, we're almost there. Let's wrap up with operating systems and applications.
Right. The main learning aims here are to understand what operating systems do and the role of different types of applications.
So what exactly is an operating system?
The operating system, or OS, is the software that manages all the hardware and software resources of a computer.
It's like the conductor of an orchestra, making sure everything works together harmoniously.
That's a good analogy. Key functions of an OS include managing files, controlling hardware, allocating resources like CPU time and memory, and providing security.
And what about utility applications?
Those are tools for maintaining and managing the system. things like disk defragmenters, firewalls, and antivirus software.
There are different ways to interact with an OS, right?
Yes, you have graphical user interfaces, or GIs, which use visual elements like icons and menus.
And command line interfaces, or CLI, which use text commands.
Exactly. GIs are generally considered more user-friendly, while CLIs offer more flexibility and control.
What are the key features that make a GI operating system user-friendly?
Things like the visual interface itself, accessibility features for users with disabilities, and the overall ease of use. Mobile operating systems are also designed with user-friendliness in mind.
What about productivity applications?
Those are applications designed to help users complete specific tasks, things like word processors, spreadsheets, presentation software, and web browsers.
Often those applications are bundled together in suites.
Right, like Microsoft Office or Google Workspace. The advantage of using a suite is that the applications are designed to work together seamlessly.
Finally, what are some of the things we should consider when installing or upgrading an OS or application?
Well, you need to make sure it's compatible with your hardware. You also need to consider accessibility features, compatibility with other applications you use, the cost, the impact on performance, and the security features offered.
Wow, that was a whirlwind tour of computer and technology systems.
We covered a lot of ground, but hopefully it's given you a good understanding of the key learning aims.
We started with the basics, explored real-world applications and issues, and then went deeper to the hardware, software, and everything in between.
We encourage you to dive deeper into any areas that particularly sparked your interest. This is a field that's constantly evolving, so there's always something new to learn.
And on that note, here's a final thought to ponder. Considering everything we've discussed, what future development in technology do you think will have the biggest impact on your life? And why? Thanks for joining us on this deep dive.